Dr. Narayan is an assistant professor in the Department of Computer Science, Electrical and Computer Engineering, University of Western Ontario, Western. He is an early career researcher who has made significant contributions in the domains of machine learning, data science, software engineering, and explainable AI. He leads the IDSL, the Intelligent Data Science Lab at Western, that spans trainees across University of British Columbia, and University of Waterloo, where he also holds an affiliate and adjunct appointment, respectively. So again, glad to have Apurva over here today, and we look forward to hearing more about him. Oh yeah, if you have questions, please keep them till the end of the talk. It's going to be about 40, 45 minutes or so, and then we'll take questions after that. So floor is yours.
Thanks, Yash. So good afternoon, everyone. First of all, I would like to thank Yash for inviting me to deliver this seminar. It's always a very nostalgic feeling for me to come back and give a talk at Waterloo, where I did my PhD almost now, close to a decade back. Not yet though, but yeah. So what I'm going to talk about today is, in general, the larger theme of the work that we do in our research group is around improving resilience and trust in AI-driven cyber-physical systems. It's a very general topic, but we are going to focus on one very specific aspect of AI systems where we are dealing with attacks on AI systems and how can we mitigate those attacks and maybe improve resilience of AI systems. Okay, let's see. Okay. So let's get started. And I think we have seen enough of AI penetration in the real world, right? It has moved beyond academia. It has moved into industry, and we now hear numerous use cases of AI deployments in an industrial setting, and be it safety critical systems or healthcare or more general settings. It is certainly dealing with complex systems, software systems, be it AI combined with cyber-physical systems, and which brings up its own new challenges and, of course, opportunities. Systems are safety critical. AI systems driving decisions in a self-driving car are expected to not make mistakes, as it can have catastrophic outcomes. Even a slightest malfunction or an anomalous behavior of the car's software or the hardware can lead to catastrophic outcomes. And the things can get even scary if you're in the air. We are now talking about self-driving drones, taxis, aircrafts, defense equipment, and so on and so forth. And most of these are driven by AI in some capacity. And as standard software systems that we have been used to be using them have known to have vulnerabilities as they get complex. And similar applies to AI softwares, which are in large-scale AI systems, which have vulnerabilities, and we need to assess them and try to mitigate those vulnerabilities. Here's a very interesting example of a use of AI in the real world. So I'm not sure how many of you have seen this news a few years back. It was great to see the use of AI in a real-world setting where in a Taylor Swift's concert in Los Angeles, they were using AI to identify stalkers. It was a fantastic application of AI in the real world. This is just one example. We know that AI can be used in, let's say, fraud detection in finance, vehicle navigation, chatbots, visual parsing, voice recognition, so on and so forth. But deep learning systems operate under one assumption that the data is drawn from the same distribution as the test set, and that causes its own challenges. Now let's look at this example. It's great to see the use of AI system to identify stalkers, but now one can create a 2D, 3D printed two-dimensional glasses that people can wear, and it can fool the AI system that recognizes stalkers. So the entire software that was used in that concert becomes unusable, because now by using these specially crafted glasses, it can actually fool the AI system. So and the entire premise of having that stalker detection system is violated now. Now, interestingly, for us, these classes may look very natural, but to an AI system, they are carefully designed so that they can fool the AI system. And now there are, of course, numerous motivations behind doing such kind of manipulations, and the incentives can be either financial, it can be based on privacy, or even malicious intentions. For example, in this use case, there was the anonymized data of travelers on public transportation was released. It was supposedly anonymized, but it was still revealing a lot of information about the behavior of people. For example, you can anonymize the data. You don't tell who the person is, but let's say if it's telling you the trajectory from your home to your workplace, in some time we can identify who lives where. So anonymization is not good enough, even when it's done well. Another one, this is, of course, in the news nowadays. Everybody is using LLMs, ChatGPT, it's in the buzz and in the news. But I don't think so it's good enough to get excited too soon. These large language models or more complex AI systems are prone to vulnerabilities. And this is just a recent article of July this year, where we have been able to manipulate the outcomes of these LLM models in a very certain specific way. And these models can have lasting impact on the decisions that we're making in the downstream tasks. So the scary part is that these models now are out in the open world and people can use it for good and bad purposes. So that's the scary part. Another very interesting example is a man in Berlin wanted to trick the Google Maps. So basically, he was living on a street and a lot of people would just drive by his street at a peak traffic hours with a lot of noise, and he was disturbed by it. So what he did is, to trick Google Maps, he kind of borrowed almost 99 cell phones and he put them in a wagon and he said, okay, I'll just walk through that bridge every day. He started doing that, and slowly Google Maps and Waze kind of thought that there's a traffic jam on the bridge. So basically they rerouted the entire traffic to side roads and the bridge was all empty. Now it's a very creative way to fool an AI system. But it's an interesting, of course, they figured it out and they started claiming that, oh, we don't use just cell phone data, we use all other paraphernalia and other sensory information to do routing. But at least this guy was able to do a good job in fooling the system. That was not a catastrophic outcome, but sometimes AI failures can have catastrophic outcomes. And I think this image is not unknown to most of you. I'm sure everybody has seen at some point in time this image of a Tesla's AI failing and causing catastrophic outcomes. Therefore, there's a need to develop robust, secure, and trustworthy functioning of ML and AI systems so that we can secure these safety critical infrastructure, and of course not have these catastrophic outcomes. Okay, so what we're going to talk about in today's talk is around adversarial attacks. The focus of the rest of the talk will be on adversarial attacks, and we'll narrow down to specific kinds of attacks. But what are adversarial attacks? Adversarial attacks are very specially well-crafted inputs that fool the AI system in its task. So it can deceive the AI system into doing something else by just giving it an input that's very carefully crafted, and that input may look normal to a human eye. And I think a very standard example is this, which kind of led to the onset of this whole field of adversarial machine learning in 2014. Goodfellow created this adversarial example of saying, when you had a machine learning model that classified that original image as a panda with a confidence of 57%, and he added small adversarial noise to it, and this image, the adversarial image, still looks like a panda to a human eye, but to a machine learning model, it's classified as a gibbon with a 99% confidence. And that's scary, because now to a human, it's still the same, while these two are very, very different. From panda and gibbon are very different entities. Similarly, in 2014, another researcher, Sagdi et al., they also came up with a similar adversarial attack where they added some perturbation to a school bus and it was classified as an ostrich. Of course, to humans, this image is not an ostrich at all, but to a machine learning model, it looks like an ostrich. Now, it doesn't stop here. These are all digital examples. But if I look at a physical example, adversarial perturbations can occur in physical examples as well. For example, these two images are printed images. The first one is an original image. The image on the right is basically a noise has been introduced on that image and then printed out. And that AI system gets fooled to recognize this as a library and calls it as a coffee shop or something else. Now, so adversarial attacks can be both digital and physical. So the focus that I'm going to keep for today's talk will primarily be on attack types that can be physical, because they are the more practical kind of adversarial attacks. And I think they're the ones which are more vulnerable and can be employed in the real world. So one of the most interesting practical adversarial attacks are referred to as patch attacks. In patch attacks, basically what you do is you take an input image, you put a small patch on it, and patch can be a sticker of a specific kind that you have created, and it fools the AI system to recognize that input object as something else. For example, on the left side, if you see, these are stop signs where there are some small patches, there are square and rectangular shaped patches that are placed on it, which causes that AI system to classify the stop sign as a speed limit sign. And that's a stationary setting where you just have a stationary image. And on the right side, what you see is a video setting where it's in a real driving setting. It's a video frames being captured. And exactly with some sampling of those video frames, you can still classify that stop sign as a speed limit sign. Now, that can be scary for people driving Teslas and other autopilot cars, because now it will recognize your stop sign as a 100-kilometer-per-hour sign and hopefully and get into a crash situation. And then that was just one example, but you can see that there can be other perturbations besides having that patch that can cause this adversarial attacks to be more stronger, for example. And it's not only on the stop signs. For example, you can see some orientation changes with patches can also cause the system fool. There's a one on the right turn. There's some where you have camouflage graffiti on there, and so on and so forth. But all of them are able to fool the AI system. So it's a very common problem and a severe problem. Another one. This one, in this work in 2019, what they came out with is if you were wearing a t-shirt of a specific design or you were holding an image of a specific kind, the AI object detector is fooled to not recognize you as a person. So on the person on the left who is holding this nice photograph in front is actually a carefully crafted patch that misguides the AI system to not recognize him as a person, while the person on the right is not, of course, wearing patch like that, and he is recognized as a person, and other objects are identified as well. So now this is it has a lot of severe outcomes on security systems where you are doing object detection, identifying people. It can mislead the AI or the machine to identify as no object and can run over, for example. I think this is an example I already talked about. You can put on these 2D printed eyeglasses and go to a biometric system and always be called as, let's say, Biden, and you will be able to enter the White House. Okay, another very practical example that somebody tried out was interesting. If you see on the front, that's actually not a pylon or a car, that's somebody actually putting on a coverall, which looks, it's an orange color coverall, and he's sitting in your Tesla over here, identifies that object as a pylon, which is not true, right? And so it might just drive by very close to it and never be able to recognize that because the person is wearing a coverall. So it's a real test of the system. Now, to summarize all of these fantastic examples that are good motivation for working in this area is the number of papers being published in the area of adversarial machine learning has been exponentially increasing. And it's primarily because as you start developing these new technologies or new systems, people are always trying to find vulnerabilities in them before you can deploy them on some real systems. So if you see, it's until 2020, the curve is almost like a hockey curve. And I think if I plot it for 2023, it will still be the same. So it's an exciting area to be in. And you can see that every year we publish more than 1,000 or 1,500 papers in this area. And these are probably only talking about top conferences, not any other ones. So just to see how the fields look like. So entire area of adversarial machine learning started in 2014. And pre-2014, basically, the objectives were only to improve accuracy. We were not looking at anything other than improving the model accuracy. And that's what an image we might have seen multiple times where everybody was trying to improve accuracy on ImageNet. We were trying to develop a model if we can keep improving the accuracy on ImageNet. And that was pre-2014. But in 2014, when Sexy et al. And Goodfellow came up with this adversarial example of the gibbon and the panda, that's where the field started, and we started seeing numerous papers that came out. Of course, when you have an attack, there's a defense. Once you create an attack, there's always somebody is trying to develop a technology to prevent against attacks, and that was when Magri came up with a robust empirical defense using something called as the projected gradient descent during adversarial training to protect the model against these adversarial examples. And the primary reason why these adversarial examples exist is these points that we see that are at the boundary, close to the boundary of the classification boundary, let's say, are the vulnerable points. And those minor perturbations actually cause them to flip across those boundaries and cause misclassifications. Of course, then people can, if somebody tries to create a defense, there has to be another person trying to break that defense. And therefore, Carlini in 2018 came up with a paper in ICLR which broke almost all the possible defenses that were created by then. And that was a wonderful attack, and it's still one of the good attacks. People know it as C&W attack nowadays. But then you see, again, people have to start creating more defenses. But to be able to create defenses, then there was a nice work called Robust Bench that came out where there's a benchmark of data set that you can test your attacks and defenses on that will allow you to evaluate how good your defenses, how good your attacks are. And of course, that's still, I would say, a little outdated by now because 2020, we have more recent benchmarks that have come out. But what is interesting to note in this timeline and significant events in this area is you have somebody trying to create an attack. There's, of course, going to be somebody trying to defend against attacks, and again an attack, and so on and so forth. So there's always kind of, I would say, there's always an arms race that we are trying to, between attackers and defenders, we are trying to resolve. But I think in some sense, it's a good situation to be in. Okay. And the challenge why we are facing a little bit of this is there's a gap between AI development and deployment. So how we develop AI is in some sort of a greenhouse lab environment. We develop these AI systems in a closed lab environment. We make sure that we tested them correctly and so on and so forth. But when we deploy them, they're actually deployed in a wild environment and where we do not know a lot about the environment. Of course, there's more things. We can look things beyond accuracy in AI. That could be around resiliency, which is around safe, robust, and private AI. Or we can also look at things about responsible AI, which is fair, ethical, and sustainable, which eventually boils down to doing things in a broader umbrella, which is trustworthy AI. Again, just this one makes me think that we are still ahead of AI. We never get fooled by those adversarial examples. Humans can still recognize what a panda is. We can still recognize that it's a stop sign, but machines cannot. So human brains perform still reasonably well as compared to AI systems. So the focus of our talk, if I look at from the adversarial perspective, there are two kinds of attacks. One is the digital attacks, which is on the left side, which is more like this perturbations or minor imperceptible perturbations that you do on the images or the inputs that will cause the AI system to fool, and those are like FGSM, PGD, C&W, and so on and so forth. They're all optimization-based techniques. They're imperceptible, and they add noise to the entire image primarily and cause the AI system to fool. What we are going to discuss today is mostly physical attacks, where we are going to look at either natural corruptions. Natural corruptions are things like, let's say, snow, dust, fog, wind, and those also cause AI systems to fool. And those are basically natural corruptions, so natural adversaries. They're perceptible. We can see through our human eye. They're also global in some sense, because if there's a fog in the environment, it will be everywhere. And they're also universal. While the patch-based attacks are optimization-based attack, because you're going to create that patch specifically for an image, they're perceptible to human eye. You can see those patches. They're localized. They're not over the entire image. And then they're also universal, that they should be valid across a range of images. So let me first talk about resilience. Resilience against natural corruption. So we were evaluating models, various deep learning architectures against natural corruptions, things like snow, fog, and so on and so forth. And we found that just having these natural aberrations in the environment can cause the AI systems to fool. So we thought, how can we improve the resiliency of these AI models? So we thought, can we do something, just augment the image with something that can improve the model's capability to classify, let's say, to a certain class. So what we did is we thought of creating some sort of naturalistic artifacts, and artifacts that look more natural. We augment the image with those natural artifacts, and hope in a way, and we trained those created those artifacts in a way that they look natural. For example, in this case, if you see these, they're small two birds that are sitting on the floor. Those are the naturalistic artifacts that were generated by our model, and that to improve the model's confidence in what it was doing. Now, these artifacts, as I said, can be used in the negative way as well. So not only I can create these artifacts to improve model resiliency, but I can also create these artifacts as an adversarial artifacts to decrease model confidence as well. But in this case, we wanted to improve the model's performance. So we can use the same technology to create these artifacts or create these patches to improve model resiliency. So if you look at this example, this is original images are on the top, where they have some of these natural aberrations. You can see the first one is a natural image. The second one is snow. Third one is a blur, fog, brightness, dust, defocus, and so on and so forth. And you can see on the top that the confidence with which your AI model is classifying those is on the top. It is still able to classify correctly, but it sometimes it's not as high as it should be. For example, in the blur case, it's obviously not even classifying it correctly. But with including these naturalistic artifacts, what we observe is it's not only classifying it correctly, but it's also classifying it correctly with a higher confidence. And that's important, right? Because when the confidence is not good, then that means the model is still not very sure of what it's looking at, right? So for example, if you look at the bottom, the second row, you will observe that the confidence is pretty high, mostly over 90%. One case where there was a misclassification, that is the blur case, it's also classifying it correctly with an 80% accuracy. How did we train or come up with these naturalistic artifacts? So we carefully chose artifacts based on the scene that we were dealing with. For example, birds, balls, which are naturally occurring objects. We chose those objects and then we created artifacts. So the primary approach was, have where we want to put an artifact. So that was a predetermined notion. Where are we going to place those artifacts? And then we're going to place those artifacts that were generated through a generative model, add those corruptions, have a classify that. And with the confidence level, we wanted to improve the confidence. We kind of did a backpropagation and, of course, keep generating those artifacts. And hopefully we get better and better artifacts as we want to improve the confidence. So that was kind of the overall framework to improve model resiliency. So here's just some visualizations of how those artifacts were helping. So if you look at on the left side, the original image, the uncorrupted image, the object under consideration was the salient object. But with corruption, what you observe is the salient region is kind of scattered all over the place in the second image from the left. And it's getting classified as a parachute now instead of a Springer, because it's just the snow has caused this to the salience object to kind of get scattered. While putting on those artifacts still tries to bring back to the original salient object. Similarly, in the second case, if you see, there's a French horn, which is classified with a confidence of 92% in the original case, but in the corrupted case, what you observe, it is still classified as a French horn, but with a 35% confidence, which is very low. While adding the naturalistic artifacts improves the score to almost 70%, that doubles it up. So that's kind of a nice thing to have. So this was some work that we started doing to improve the resiliency of AI models using naturalistic artifacts. And we could have non-naturalistic artifacts as well, but this just wanted to, keep naturalistic because of the image doesn't look very absurd after adding those. Now, we are going to talk about one of the other works that we did was around introducing multi-patch attacks. So what are patch attacks? I think I briefly talked about patches in the few examples that I showed, but this is another example that's very common for an aerial imaging setting. So if you want to hide, let's say, your defense airport, you can camouflage your aircraft with a very specific design on top, and your aerial imaging system will be fooled to not recognize them as aircrafts anymore. For example, if you look at in this example, the aircraft on the second row from the bottom, the second one is not identified as an aircraft. And that's primarily because there's a small patch that's being placed on top of that aircraft. It's on all the aircraft, however, that one, it's not successful. Again, the success rate of these attacks can sometimes be very variable, and that's why it's such. Again, this is an example I already talked about. I'm not going to talk about it again. And same as the other one around autonomous driving example. Now, let's see what are we trying to do in creating multiple patches. So the work that has been done so far revolves around putting a very well-trained patch on an image anywhere in a random fashion. And the hope is that you're going to fool the system. It's been successfully studied, and there's numerous papers out there. We thought, what if we cover the same percentage area of the image, but now break that patch into 4 small parts? So now we have the same patch, but now it's divided into 4 smaller patches and placed at different places on an image. That's one kind of multiple patches, and we called it a split patch. Another one could be saying, I trained 4 small patches synchronously. So I'm not going to split one larger patch, but I'm going to train 4 smaller patches, and I call that as mono-multi attack. And those 4 smaller patches are then placed randomly. In this case, 4 is just an example. You can have n number of patches that you want to train. Or I can have 4 small patches, all of them different, and they are trained synchronously to attack the image. And we call that attack as a poly-multi attack. So if you look at this, this is kind of the multi-patch training framework, where you have a set of images that you want to train on. You have models on which you want to test those images. So there's going to be multitude of those models. They can be, let's say, ResNet, VGG16, VGG, or ResNet 18, and other models that you want. You can have all those models, and you can have these patches that are being generated with going through a whole cycle where you train these patches on different models and come up with a patch that's robust against majority of these models. The whole cycle tries to generate these patches. The only thing that we had to change was depending upon what size of patch that we want to create. And these patches can be of various sizes, but also the positioning is all random. We are not really at this point looking at where should these patches be placed to create an adversarially strong attack. The positioning is still under question, and I'll talk briefly about it later, but for now, the patches are just placed randomly anywhere on the image. And to this procedure, we are carefully coming up with a patch that would work. We start randomly, but then we come up with a nice patch. And these, if you look at these images on the right, these are trained patches. These are patches that have been trained, and they have shown to fool the models, majority of these models. So let's look at some results of our work. So in this case, if you look at we talked about 4 kinds of attacks, which is a single patch attack, split attack, mono multi attack, and poly multi attack. If you look at the poly multi attack, the last one, what you observe is, and then let's look at the last column where we are talking about the perturbation area of 4%, in which that means the patch size is of 4% of the total image size. On 3 data sets we tried, and the adversarial accuracy was 71% on Eurosat. The adversarial accuracy was 2% on ImageNet and almost 52% on CFAR10. And that's better than, of course, any of those other attacks. And those single patch, split patch or mono-multi attack. And if you look at, as we increase the perturbation area, if you go from, let's say, 4% to 8%, you see the strength of the attack increases, of course, because now you are covering a larger section of your image. The strength increases and it goes almost to, you see in the first case, 25% adversarial accuracy, 0% for ImageNet, and 14% for CFAR10. So that's a very strong result already. That means any of those single patch defenses hopefully should not work in this case. And that's, we're going to see in a bit how that works. Okay. This is another result where we are looking at so the first results were with VGG16 architecture. The second results are with the ResNet 18 architecture. And again, if you look at just the bottom line, it's, of course, one of the most strongest attacks. And if you look at the first one, the 12% area, the accuracy is almost 0% for all the 3 data sets. Doesn't matter. That means your attack is extremely successful and the model is not able to decipher between an adversarial, is not able to classify the image correctly, right? So let's just look at some visuals on how and what's happening when we are introducing these patches. So if you look at, on the first column, we see an original image. Second column is around the non-attacked image. So we're looking at the saliency map of the unattacked images. Now, if you look at the single, split, and mono-multi attack, you see the saliency region kind of gets hovered around the patch where it is. While if you look at the poly-multi attack, because the patches are somehow trained synchronously, they are somehow related to each other, the saliency region is spread and is somehow connected with all the patches. And that kind of causes the model to fool around identifying what the object of concern is. And that's why it's probably one of the strongest attacks that came out of this work. And if you want to look at, for example, the number of patches, the trade-off between the number of patches that you want to have and the accuracy, you see for the number of patches, as you increase for poly-multi attack, doesn't matter, the accuracy is very, very high. And you see there's a small decrease in the accuracy. The attack success is primarily because you're covering a large section of those areas. And that's why, you're not just able to do it in a synchronous way. And same as with the mono-multi patches also, as you increase the number of patches, slowly the accuracy attack success rate reduces because you're now dividing the entire patch into smaller chunks. But let's look at the performance against the state of the art. So we wanted to see, okay, great. Let's see how our attacks are doing against the defenses that exist at the moment. So there were two defenses. One is known as a patch cleanser, another one is the LGS, that were for defending against patch attacks. And what we observed is, yes, the original without defense accuracy of the models were around 93%, 99%. So all of the models had a very good accuracy over there. But if I look at just employing the defense, the accuracy drops, even if it doesn't have an attack. So if you look at the first column, the original one, we do not have any attack on the image. Just by employing the defense, your accuracy has dropped a little bit. And that's just primarily because the defense is trying to, it's getting the system more complex. It's probably overfitting a little bit. And that's why your accuracy is dropping. But when you start looking at other cases, when you're looking at a single patch attack, without the defense, it's for the larger cases, 0.2% and 12%. While with defense, the accuracy jumps up to 43 and 52%. That's actually a good defense, right? It's taking it from 0 to 43%. If you look at the last row, which is perturbation of 4%, you observe that it's jumping from 71 to 78%, which is pretty good. And so the defenses are working, what that's implying. But let's look at the last one, which is the multi-patch one. Without the defense, the adversarial accuracy is almost, we just had 0%. That means you're not able, the model is just getting fooled with the multi-patch attack. So the patch attack is working well. But even with the defenses, the accuracy is not increasing. Your accuracy is still at 0%, 0.1% for both those defenses and so on and so forth. Only in the last case, where perturbation is 4%, with LGS was able to improve the accuracy from almost 1 to 16%, which is still okay, but not too great. So that means the multi-patch attacks was kind of the state of the art in some sense and breaking all the defenses that we had. And so these are the similar results for BGG16. Those were the results for ResNet 18, and both tell the similar story. Now, what are the defenses against patch attacks? So of course, there is a large number of defenses that have been created, people have been working on against patch attacks. And most of them are focused on single patch attacks because we were the first ones to propose multi-patch attacks. So most of the defenses that we saw at that point in time were based on single patch attacks. So some of them are based on saliency maps. Some of them are based on adversarial training. Some of them are focused on small receptive fields, certified defenses, which are more complex, very good defenses, but are extremely computationally expensive. And there were, of course, a bunch of other kind of defenses that were there. What is interesting to note that most of them would fail against multi-patch attacks. For example, certified defenses are one of the strongest defenses that you can have. They're guaranteed to provide you with defense. They're extremely computationally expensive, but they fail against multi-patch attacks. Same was with small receptive fields, failed against multi-patch attacks, and so on and so forth. So if all of them were unsuccessful, what can we do? So we came up, of course, we were kind of the ethical hackers. We were creating attacks, so we wanted to also create a defense. So we looked at what is the underlying property of patches. And what we observed that patches, wherever the patch was, it was clipping the image values to 255 because there was an abrupt change in the pixel values in the location where you had patches. So what we did is let's include something known as total variation loss that says you want to look in the vicinity of a certain number of pixels and see what is the variation between the pixel values. So this would allow us to determine the complexity of image to its spatial variation. And we used something known as total variation-based image resurfacing that we clipped off those patches or smoothed the images on the areas where we found high variance of pixel values, and then tried using the model. And I'll show you in a bit how it looks. But the advantages of using this technique was it was model agnostic. I just needed to look at an image. I didn't need to care about what model are you going to use that image. It was task agnostic. I didn't care whether it was an object detection task or a classification task. It was agnostic against the number of patches. You could have 1, 5, 10, 15, 100 patches. It was agnostic of that. The patch location agnostic. It doesn't need to know where the patch is. It will identify it by itself. And of course, it could help you in detecting where the patch is based on the properties. So how does it look like? So if you look at the surface of the images, what you'd observe is wherever the patches were there, we would see something like that, a spike in the pixel values, primarily because when you're creating those patches, the pixel values get clipped up to 255. And so that's why you always saw a spike there. Of course, if you have an entirely black or a white image, that would be very different, but still in a normal images, we saw those kind of spikes. So what we did is we saw that anomaly and we would resurface that. So we'd clip it off and see how the image looks like and then try to run it through the classifier. So the TVR framework, so you had an adversarially patched attack image. We would look at the 3 RGB channels there. We would look at the block-wise total variation. So we chose various block sizes and look at the variations. And we saw that in all the 3 channels, we would see that spike of where the patches were. And now it makes it easy, so we can now use some sort of an outlier detection approach to resurface those spikes. And then we had these cropped images where we had some of these patches being removed. If at this point we would say we don't, those blocks where we found patches, we just colored it with black, let's say. Or we could use some sort of an in-painting technique to reconstruct the image and hopefully then try to identify the class. So either way, I'll show you results about both. But the interesting thing was with TVR, we were able to defend against all sorts of multi-patch attacks. And if you were looking at an ensemble of models, then of course the accuracy was much better for adversarial accuracy as well as for target accuracy. So this is an interesting one. So again, we wanted to compare our work with the other defenses. For example, just naive accuracy, LGS, patch cleanser, and ours. We were actually able to beat almost in all the cases of multi-patch attacks. Of course, in some cases, we were at least to the state of the art for single patches. Of course, those patch cleanser and LGS were designed for single patches. So we were able to meet at almost the state of the art, most of the cases, but in multi-patch, we were way better than any of those defenses. If we look at the 2 points where, let's say, if we in-painted the images, and once we did not in-paint the images, in-painting just improved the confidence by a little bit because we were trying to reconstruct the original image so it helped improve the class accuracy of the. While if you are not doing in-painting, it's still much better than the naive accuracy that we have. So if you look at this plot, the red line is just the accuracy without TVR. Then the blue line is with TVR without in-painting, where we're not doing any reconstruction of the image. And the green line is TVR with in-painting, where we started doing some reconstruction over there. So here's some visualizations again. So if you look at the images on the left side, you see where the patch is, you will see a spike in your image intensity values. We would just clip them off, do some reconstruction, and I'd then use that image. While if you look at wherever the patches are, it doesn't matter now where the patch location is, we should be able to find some sort of these spiky behavior in the curve. For example, in the last one, we have 4 patches, and where you can see those 4 spike points. Here is some clear visualizations of images, what happens. So for example, if you look at the first row, the first example is a class is a golf ball. We place a small patch on the golf ball and it gets classified as a coordinate, and it's a targeted attack. So the patch is supposed to classify that golf ball as a coordinate. So what we do is once we identify where the patch is, we do some cropping. So we remove the patch, we mask it, and then we try to in-paint the image. And if you look on the right side, you have a kind of a reconstructed image of a golf ball. But even without in-painting, the classification results got better, and with in-painting, it just got much better. So same as in the second case, the same patch that we were using on this fish tench, and you'll see the patch causes the fish to be classified as cornet, and the same approach applies here as well. In this case, it's again the same patch. I'm using the same train patch on different images, and it's misclassifying them. What we did eventually was we wanted, of course, let people use it. So we created a tool that now people can upload their images and try out different attacks on them and see how our defense works. So now this work actually just got nominated for the Best Paper Award at WACD. So that's a good thing. Also, we wanted to move a little beyond, just because all of the work that we were doing so far was on digital images, right? So images and the patches were all digital. We placed the patch. Now this is something more physical. So we said there was a data set that gave images in which these patches were not digitally placed on the image, but they were actually printed out from a printer, cut, and then placed on these objects. And they started, we can see that how they get misclassified. For example, the target class is on the top and the predicate class is this. So most of the cases we were able to reach the target class with the physical patches. For example, the soap dispenser one we were able to achieve, while Cornet, yes, was a very good attack. Cell phone was a good attack. In some places, of course, we were not, the attack wasn't successful. But with TVR defense and without in-painting, so now we deploy TVR on it, without in-painting, every time we were able to, most of the time we were able to get it to be classified correctly, besides, I think, the last one. Again, because I think if you observe, there's so much of, it's almost like black image, so it was hard to identify, differentiate between a patch and the original image. Okay. So let me just summarize the work that I just talked about. So we were looking at the physical attacks primarily that can be done. So we looked at some natural artifacts or natural corruptions that happen in images that cause AI models to fool. And those were like snow, dust, blur, and brightness. And we created natural supportive artifacts to improve resiliency of the models. While then we looked at patch-based attacks, where we created a notion of multiple patch attacks or multi-patch attacks, and then created a defense that is kind of generic as so far that can work against any kind of patch attacks that we have. So to summarize, of course, we kind of bring up the potential uses of multi-patch attack systems. It can mislead the AI systems in their decision-making. Of course, there's a myriad of possibilities of multi-patch attack variants. Something that we are currently working on is the location of patch to make the patch attack more severe. And we have had some initial success in there because it's highly dependent on where you place the patch. Of course, as you propose a new defense, it always helps the attacker to come up with a new attack. And that's an ongoing race. We need to keep fighting with it. So there's always exists an arms race between attackers and defenders, and we are in it. Hopefully ethical attackers and defenders. I would like to acknowledge all my industrial partners and funding agencies. They're for all the projects, not for just this project, but especially these students who have worked on various aspects of this project in the past year and a half. Primarily the first one, Abhijit. He just finished his master's. Most of the work that I presented today was a part of his master's thesis. Others were interns and they came and go. And I think I'm happy to show that Abhijit is now at Waterloo. And so that's a good sign. Thank you, everyone. Of course, I'm always open to emails and conversations around collaborations. And of course, always looking for good master's and PhD students. Thank you so much. Okay.
Let's take some questions from the room. And for the folks online, could you just announce that maybe they can raise their hand and ask questions?
Yeah, anybody online can ask questions. Sure, let's see.
We can start.
Hi, Nas.
First question.
Yeah.
Thank you for presenting the very interesting work. About your defense, because I'm not a computer information processing, might be a very simple question. When you say resurfacing, if you go to defense, what that means, how you could identify that anomaly that we have a patch? What that exactly?
So resurfacing is primarily just clipping off where we found that spike. So we clip it off at the maximum value where the rest of the image lies, the maximum pixel values, we just clip it off there. And now we have identified where the patches, and now we first initially just clip it and make it black. That's all we do there. We just, because where the spike was, we know that that's an anomalous portion of an image.
And the other question, I mean, you mentioned you are still working on the location.
Yes.
Have you found
yes. So that's a good question. So location of a patch is a very hard problem because again, there is almost infinitely possible places where you can actually place a patch in orientation as well as location on an image. So what we've done is we tried some sort of an evolutionary algorithmic approach to let it run and find out what are the best possible variations, because this is something that we don't want to do on the fly. We can let it run for hours together and tell us, okay, top 10 placements of patches, both from orientation perspective as well as location perspective. So we have been able to, we are reasonably successful. I think we are able to, and this is an ongoing work, but we have been able to come up with, let's say, 10 places where we know that certainly it's going to be a strong attack. So far, both from orientation perspective, and even in the orientation, that's an interesting one, because we are not only causing it to have, let's say, orientation changes just about rotation, but we're also trying to squeeze it a little bit. We're trying to stretch the patch also a little bit and to see if it is more effective or not. And we are finding that it is actually reasonably effective, even if you modify the patch a little bit. If you do too much of it, yes, it gets violated and doesn't work as an attack anymore. But we have been able to see so far that a little bit of perturbations to the patch also are very useful to create stronger attacks. So hopefully let's say in early next year, we should have some concrete results around that.
Yes, orientation also somehow related to the shape, right?
That's correct. That is correct. Absolutely. So if it was a circular patch, we are only trying to stretch it and it become an oval, or for example, right? Yeah.
Thank you.
Yeah. Thanks. Yeah.
I have some question. The question is that related to your work. So you said that you kind of like take the patch and then try to either make it black or add another.
Yeah.
So like my question is, if there's something like a screen in your picture, like a mobile phone,
Yeah.
and its screen is actually the patch, and we don't want that to be removed actually. Your algorithm is find it as a patch and it will just make it black, and probably it won't be categorized as a mobile phone. What would you do then?
So you're absolutely right. That's absolutely right. So if it was, so one thing that you'll observe interesting is patches will never be always black. Patches will have a variation within the pixel. So if there's no variation, that means it's completely black. Then it's a part of the image.
No. What I'm saying is like honestly, like the default, for example, wallpaper.
Okay.
Like that.
That's an interesting one. We haven't tried that out, but that's a very good. Let's see, we can try it out probably. Yeah, that's a good point. So if we have a patch that's on display on the cell phone, how does it work? Yeah, I see a point. No, good. We haven't tried it out, but hopefully we will take our technique will clip out that portion of the screen most likely.
Like another one is that what is the threshold that your input is an adversary versus, like you mentioned about this picture that Tesla was like someone has been wearing something and this, okay. So if I, for example, wear like the clothes of a mouse and the model kind of like categorizes me as a mouse, that means that the model is actually doing a good job.
That is correct.
Okay, so what is the threshold here that I can say this is an adversary versus this is a good output for me?
So if now there are two things. You're asking a very good point, right? It's about reliability of the model. The model is doing a good job, but is it good enough for that application in which the model is being used, right? So if the model is saying, yes, it's a mouse, that's great. Your car can probably drive over the mouse. But it has to also have more knowledge around the domain that model is being used in, right? For in the traffic or the car setting, mouse cannot be of a size of a human being. It is still classifying it as a mouse, that's great, but it cannot be that big, right? So there's more domain knowledge that will come into play to allow the system to be secure and make sure that your car doesn't run over you. Sure.
So the thing is, two more. One of them is that if an algorithm has like a pre-processed data for the image, how can you make sure, as an attacker, how can you make sure that your image will be categorized as an image and not just thrown away on the first run?
That's a very good point. So I did not talk about those kind of attacks. So there are other kinds of attacks which we call as data poisoning attacks, or there's attacks in the data itself on which you're training the model. And yes, so we have another range of techniques that we can use to mitigate the effects of, let's say, training data faults or issues in the data itself, which is pre-processed, right? So for example, you could do an ensemble approach where you not have a single model, you have an ensemble of models, and hopefully the ensemble always does a better job than a single model. So there is some work that we have done around what we call as soft errors. So mitigating soft errors. So forget about what soft errors are, but the approach is, I know if one model classifies it as, let's say, a human as a mouse, the hope is that 5 other models will not classify that, or at least 3 of those will not classify that. And then we'll use an ensemble approach to address those kind of issues.
Can you repeat your last question for the vulnerability? Thank you. Are there any other questions?
Yeah.
In both of your cases, so you have the natural as well as your batch attacks, right? And in some sense, both of them are kind of adversarial. It's just the source.
Yes, that's correct.
One of them is natural source, the other one is injected.
That's correct.
So with your multi-batch attacks, was there any reason why you didn't use the same sort of generation method as you did for the natural approach to generate your artifacts or something? Because the final batches that you converge to by your training losses are essentially kind of like noisy.
Yeah, very good point. So we did try that, by the way. So we did try using the same approach to create multiple patches on the naturalistic artifacts as well. It's just that those were already, they were not as strong attacks as these ones. We tried that. We initially wanted to do that ourselves. So you can have multiple birds in the image and fool it around. Yes, we tried that. Good question though. Thanks.
So I think that brings up a question that I had as well. Like you said, this is cyclical, right? Someone comes up with an attack, this is an attack. So now your defense is based on total variation.
That's correct.
How would you attack that?
So for example, to attack that, we can always create patches which
maybe blend in, but if they blend in.
So it's interesting. So we tried doing that also. So we did that for medical imaging. For histopathological images, we created patches that would blend in, but to us as humans, we can certainly see that there are some specific artifacts, but it would still look like a, let's say, tissue. And those were not easily detectable by us. So I did not show those results, of course, but yes. So if you do in application domain, it will be affected. Yes. So it's not I would say it's not obviously 100% a defense, but yes, there are weaknesses there too. Yeah. Any camouflaged patches will not work. Yeah.
Were there any questions online?
Let's see. No.
All right. If not, let's thank Apurva again. Thanks, Apurva.
Thanks, Yash. Thank you.